Hello. The first system we are going to try to control is a simple gain and low pass filter, or a gain with one pole or time constant as seen here. And what we're going to control it with initially is with a proportional gain, but we're going to have try three options. One's going to be proportional only, one's going to be integrator only, and one's going to be proportional integrator together. And obviously the proportional integrator together is the only option that is practical, but I want to cover the other two cases first. To start with, we have the plant, and then we have the proportional only controller, and I have to make a substitution into our closed loop transfer function here. So I end up with this. Then I can simplify, and notice there's only one pole. There's an S and then a constant here. So this is the characteristic equation, and since there's only one pole, there's no chance that it's going to oscillate. Maybe in a practical application there would be some unmodeled poles that are very high up and you could make it oscillate, but chances are you wouldn't be able to make this one oscillate. I'm going to use the same gain and value for the time constant, or in this case the bandwidth, for all three examples. I'm just arbitrarily choosing a gain of 10 for my proportional gain, and that's the percent output for, see, that's the speed, 10 millimeters per second per 1% output. And then I've got the time constant, or the sample time, and then I'm going to use the same model for all three examples. I'm going to this is the model for the low pass filter with the gain, which is basically the model for our plant. And one of the things I want to point out is that because there's only a proportional gain, the closed loop gain is always going to be less than 1. And you can see that as S goes to 0, that K times alpha times Kp over, this is going to be 0, alpha plus K times alpha plus Kp is always going to be less than 1. And you can see that calculation down here. The gain is going to be 0.96, which means if we tell it to go 100 millimeters per second, we're only going to see it go at 96.7 millimeters per second. This is my simple proportional control. This updates the model. So this updates the velocity. I have the control output, the previous velocity, the next velocity, using these coefficients calculated up here. And then we have a proportional only gain, and I'm limiting it to plus or minus 100%, and I return the velocity and the control output. These are the step jumps I'm going to make. Now, normally in a real velocity system, you're not going to want to make step jumps, but I like to do it just because it's simple and I can see how the system's going to handle saturation. And in this case, you can see that the output does saturate at plus 100% here and minus 100% here. The control output is the green. You can see the light blue or cyan is the target velocity, and the actual velocity goes right up to about 96.7%. It doesn't quite get there, and then it ramps down to almost minus 200, and then it's a little bit less than the 50. That's pretty obvious, and then you notice that the time scale here is only 1 second, so it's pretty fast. I'm going to do a Bode plot. You can see the bandwidth is pretty good because we have the gain cranked up pretty high, and we could get away with that because there's not much chance of oscillating. And you can see that the phase lag is minus 90 degrees because the closed loop transfer function only has one pole. Then I'm going to plot the poles and zeros. There's no zeros in this system, just one pole. There really isn't that much to talk about in this system, except for the fact that it's not very practical because the actual velocity will never reach the target velocity. And this would also apply to applications like temperature, where you have a first order plus dead time, and without having an integrator in your loop somewhere, you'll never reach the set point. The process variable will never reach the set point. So that's it for the proportional only control. And now I want to switch over to the integrator only control. This provides a few more options. We have the same plant, again with a time low pass filter, or basically you could say this would be like a op amp, an RC op amp with gain. And here we have the integrator only. We make the substitutions into the closed loop transfer function. And what's significantly different here is that we have 2 poles. And that's going to give us 3 options for control. The first option is going to be underdamped, and then we have overdamped, and then we have critically damped. And what I'm going to do is I'm going to change or use only the critically damped, because I'm going to get the best response. You can see that the gain here, the poles here are going to have, the real parts are going to be at 1/2 alpha, no matter which one I choose. But if I choose the underdamped version, I'm going to have a real or an imaginary term to my closed loop poles, and that's going to cause overshoot. And if I'm going to have the same settling time, why choose the version that's going to overshoot? So here I should get a nice critically damped system. Now let me show you how I get this, because this is a little bit different. To calculate the gains, what I have to do is equate the powers of S. So I start out with the 0 power of S, that's this here, and I have to equate it to the 0 power of S here. And then I have to equate the first power of S, the alpha, to the first power of S in my desired characteristic equation here, and I can solve for that, and this is the equation I get for Ki and lambda. Now we've got to remember my poles are located at minus lambda. So I've done the same thing here for the critically damped response. So this is the formula for the integrator gain, and this is the formula for the poles. There's going to be 2 poles. And you can see that this is not very far to the left, so the response is going to be very slow. I'm going to use the same parameters as before. I'm going to calculate the integrator gain. This is very low. Again, the pole is not very far to the left, so the response is going to be slow. This part is identical to what I did in the previous proportional only. This is my integrator only controller. So this is actually updating the actual velocity, and this part here is doing the integrator update. And then I return the control output and the actual velocity and the control output. I'm making the same jumps here for step changes, but notice I'm simulating 10 seconds instead of 1 second. And the reason why I have to do that is because the poles are so close to the origin, the response is not very fast. So in the previous examples, the whole simulation was in the first second, and here I need 10 seconds to be able to get the integrator to wind up to get to 200 millimeters per second. But notice it doesn't overshoot, and that's just as predicted. I'm going to plot the Bode plots. You can see the bandwidth is very low. The proportion only went out beyond 10 before dropping down. Also notice the phase lag starts out at minus 90 degrees because there's an integrator, and it goes to minus 180 degrees because there is 2 poles. Now I'm going to graph the poles and zeros, and there aren't any zeros because there's only 1 gain. And you can see I have the 2 poles at minus 3. So the big thing to get out of this is the integrator only is very slow, and the you can get you have a choice of 3 ways of tuning up your system, and obviously the best way here is critically damped, but it's still not practical because it's just too slow. Next is the PI control.